Hello, so today the goal is to train a YOLO 11 object detection model and prove I can run it in two ways. The original PyTorch model, and after converting it to ONX, I have to run it on ONX runtime as well. And after that, there is an optional challenge of comparing the IOU of both of the outputs. So first I will start with creating the virtual environment for Python and also creating the requirement.txt for it. So I will do it using Claude. So I will set up the VNV with requirements.txt Ultralytics for running the YOLO model, and ONX for converting the model to NX, and ONX runtime for running it natively on ONX runtime, and matplot library for drawing the comparisons onto an image for IOU, and probably we will add speed comparison as well in it. So first let's start with only predicting the output with YOLO 11 nano.pt model. So I'm just going to create a predict.pt.py that loads YOLO 11 and run it on image.jpg. After that, just for the console logs or for the debugging output, we will print each bbox and labels and the confidence score. Then we will save the annotated image as an output, and also the raw detection in a JSON file that we will use for comparing it later on. So annotated pp.jpg and detection to detection pt by .json. So first it is going to create the virtual environment, and after that it is going to read our requirement.txt to install all the libraries that it requires. So it has created the requirement.txt and added all 4 dependencies. I'll add other dependencies as we go through if I think I'll need it. So it has created the virtual environment directory, and we will use this version of Python to run this. Okay, so it is still writing. I think probably it is installing the libraries right now. We can review the code when it is installing the libraries. So we are importing JSON for outputting the raw detection or in the JSON file. Then we are importing YOLO for running the model, and then we are running the prediction on our model, and we are giving this image.jpg as input, and then we have a list of detections, and we are looping through the result dot boxes to find out all the boxes that our model has predicted. And for each model we are extracting the x1 y1 x2 y2. So x1 and x2 is the starting and ending edge or points in horizontally for the box, and y1 y2 are vertically edges that creates the boxes. And here we are extracting the classes for the each detection with the confidence score we are getting and the label. So the model stores the classes categories numerically, and then we have to run this to map the classes numerically that are saved in the model. So we can have output names as car, human, giraffe, and not as 0 1 2. Then we are just printing it out for debugging purposes here, and after that we are just creating this object detection. We are just append appending it to the detections as an object, so we can later save it as a JSON file. And here we are saving it as output with the annotated images, and here we are dumping it into the JSON file, the object, and we are just printing it out here. And I think it is running it right now using the virtual environment. And the output is here. It is done. So it has detected two giraffe, two cars, a driver with label giraffe. As I said, the model saves it as an integer number, so we have to map it to the original class name. And then we have the confidence score of that detection with the b box x1 y1 x2 y2 as the values here. So these are the pixel values to create the b box on that image. Yeah, we can see the output here. So we have the two car, one person, and two giraffe with their confidence score. Sorry. So now it's time to convert this model into ONX and then run it on using ONX runtime and check the output. So I will clear this. So we don't waste more tokens. We should be clearing the context, so that's why I have done it. Now I will just so now I will write the file for converting this PyTorch model into ONX model, and then we will run it for inference on image.jpg to get the output same as we have for the PyTorch model. So I'll write the prompt as convert and infer onx.py, then export the YOLO11n.pt to ONX model, then load the YOLO11n.onx and run the inference on image.jpg. maybe we can mention the file here so it doesn't go out to waste tokens on searching the file. Now print each bbox and class or label and confidence score, then save the output as output onx.jpg and the raw detections as detection onx.json. Run it and confirm detection are working. So now it is going to read what we already have done and create a new file that will take the YOLO 11 nano.pt and convert it into an ONX model. Then load the ONX 11 model, YOLO 11 model using the ONX runtime and run it on the image.jpg to print each bbox, label and confidence score. Then save the output as output onx.jpg and the raw detection as the detection onx.json. So it's already done. Here is the complete code. We are just exporting PyTorch weight into ONX and then we are loading the ONX model as detect and running it on the same image, and the same process again. We are getting the x1 y1 x2 y2, the class, the confidence, the label. We are printing it all out and then we are appending it into the detection list as an object for later dumping it into our JSON file. And here are the JSON file with the same class, ID, confidence, label, everything, and the output is here. It's pretty much the same. So now our task is the optional task of finding the IOU and comparing the IOU, and also we can compare the speed as well. So again I will clear the context and then I will write compare iou.py with matplotlib draw image.jpg side by side, draw PyTorch boxes in green color on the left side and ONX boxes in blue on the right side. Also add label and confidence score on each in the same color as the box. Match each PyTorch box to the closest same class onx1 and show a table below with confidence for both and IOU interaction over union per object plus the mean score. We can also benchmark the speed so for both of the models, so also benchmark inference speed for both. Warm up each runtime, measure it for 30 runs and report PyTorch and ONX average latency and FPS. Display this metrics on comparison dot jpg and save it. So now it is going to draw the PyTorch output on the left and the ONX output on the right, and we will have the intersection over union and also the speed latency of both models. And yep, now we are just waiting for it to create the script and execute it. Okay, so the test is already done. The mean intersection over union score is 0.996. Okay, just for the information, the score is in between 0 to 1 in the range, and the higher it is, the closer it is to the, so the output is like the same. And here are the results. So the PyTorch edges out ONX on CPU. Currently I'm running it on MacBook M1, and the PyTorch model is running a bit faster than ONX model. The results are here. For PyTorch, it took 33 milliseconds for one inference, and it did 29 frames per second, and ONX took 37 milliseconds over 26.9 fps. And the comparison is pretty much the same. Here we have the output, and it is showing the YOLO 11 PyTorch detection on the left side and the ONX detection on the right side. And here we are comparing the score. So here are the categories. It has printed the inference speed on top of the table. We can fix that, and I'll do this after explaining this. Here we have the confidence score for each of the categories and a mean score of intersection over union here. So it is pretty much detecting the same on PyTorch and ONX side. Now I'll just fix this thing, like this box should be under the table, not above it. So I can say it here. keeping it in the same context, is showing the inference comparison but drawing it above the intersection union table. Please move the speed comparison below the table. So it is fixing the height ratio. Yeah, this is much better than before. Now we can see the inference speed here in the output. So yeah, that's it. That is the summary.